So good afternoon, and this is April the 1st. This is not an April Fool's Day joke. We are going to be doing statistical mechanics, and I'm now going to silence the what happens when the participants enter, so we don't have those annoying chimes. All right. So let's backtrack about what we were doing last time. So we started on talking about computer simulations, not computer simulations. Forget about that. I've got computer simulations on the brain because I'm simulating COVID-19. All right. Last week what we were talking about last time was systems with interactions, which is kind of the same thing anyway. And what I was showing you was a way to study the equation of state of an interacting system using the Virial theorem. So what we did was we started off by writing down what the Virial theorem is, as shown over here on the left screen. And what we considered was a particle colliding with a surface. And we imagine that that happens. The surface is made up of small elements, ds, with a vector pointing outwards. So in here is the gas, and here is the container. And what we did then was we wrote down the virial shown over here, which is simply q times dp by dt, where the dp by dt is of course just the force from Newton's second law. And then from that we wrote down that the force is just related to the pressure. The pressure is force per unit area. So the force then is the pressure times the unit area, and this little element of area where the particle is supposed to have collided, what we need to do to work out the total pressure is we need to sum over all the forces of all the collisions. So we're going to so what we're going to do is literally coarse grain this type of collision over the surface of the container. So we're going to be summing over all the particles. And so when we look at the positions, those then, of course, turn into R. So that's the positions over here. The forces are just replaced by the pressure times the surface area. And then we sum over all little elements of surface area. And then what we did was we used the divergence theorem. So the divergence theorem says that if I have a vector times an element of surface area integrated over the whole surface, then what we will get then is an integral over the volume of the divergence of that vector. And the divergence of the vector r is just d by dx, d by dy, d by dz, acting on the vector x, y, and z. And so dx by dx is 1, dy by dy is 1, dz by dz is equal to 1. And so what we end up with is that this integral just gives us the value 3. And it gives us the value 3 for this, and then a factor of the volume of the system because of the integral dv. And so what I've shown you then is that the virial is minus p times the volume times 3, and from the virial theorem, that is just equal to minus nkbt, something which we proved back in the dawn of time. And so we then have a very succinct derivation of the ideal gas formula. So that's where I want to start today's lecture. There's my little cloth, okay. So today is April the 1st. And what we're going to do is we're now going to look at what happens when we have a non-ideal gas. So this is now part 2. We're going to use the Virial equation of state for a non-ideal gas. So Now what we have to take into account is the fact that there are two types of forces. So the first are the ones that we already considered, which are the particles colliding with the walls. But the second is the interparticle forces, and we're going to assume that those arise from the two-body interactions. So we're going to write down then the Hamiltonian. It's just the usual thing, it's just the kinetic energy. So that's what we had before, and now we have a new term, and the new term is not that. The new term is the potential energy, which I'm going to write in the form U of Ri minus Rj, summed over all I not equal to j, so that's to make sure that we don't have a particle interacting with itself. And then this factor of 1/2 is to prevent overcounting. So sometimes we'll write it like this, sometimes we might write it as sum over I less than j. And then what we're going to define is the vector Rij to be just the vector Ri minus the vector Rj, and Rij without an underline, without a vector symbol, is just going to be the magnitude of this. So what we're going to say then is that the virial, which I'm going to try to write in this sort of curly fancy V form, is just the ideal virial plus some perturbation, and that perturbation is going to come from the interactions. Now the ideal virial, that came from this term over here, so this is the term that contributes to the ideal part, and then what's going to happen is that this term over here is going to be due just to this part. So now let's go and work out what that is. So delta V, not very good at drawing curly V's apparently, not at least not today, I'm going to write as minus 1/2 the sum over I not equal to j, Ri, dotted with du by dri, and u depends on Rij. Now what we're going to assume is that we are dealing with a system which only has central forces, and so this term over here is just this absolute value of Rij. So we're going to assume that we only have central forces, and so everything is spherically symmetric. Okay, so now I'm going to do a rather boring set of manipulations to beat this equation down into something which is a bit more useful to us. So let's just say it like this. Next, some cosmetic algebra to reduce this expression to a useful formula. And what I mean by useful formula, well, what I mean is that once we've done that, what we're going to see is that this useful formula actually involves the two-point correlation function. And we talked last time about why we expect the two-point correlation function to come into the equation of state, because the two-point correlation function describes how the probability of a particle being at one place in space, what is the probability of finding another particle nearby, and that probability will then influence the correlations, but the particles being interacting will also cause them to make a change to the pressure that they exert on the walls because of their long-range attractive forces. So we expected from our sort of hand-waving arguments last time that this would involve the two-point correlation function, and we're going to see that that is the case. So what is the strategy? So the strategy is to take the contents of delta V, this fancy V, and we're going to express them purely in terms of Rij. Okay, so this is going to be a little bit tedious for the next few minutes, but so when you wake up, I'll announce it loudly so you can see what the important term is. So let's write this in the following way. So let's put this in a slightly different color so that we don't mistake it for anything important. All right, so what are we doing? So we're going to start off by saying du by dri. And we know that this thing actually depends on Rij, so we can simply write this as du by drij times drij by dri. And when I write down dri, what of course I really mean is just the gradient operator. So d by dri, by that I mean d by dxi, d by dyi, and d by dzi. Okay, and I goes from 1 to n, and the same for j. Okay, so let's focus just on this drij term. Now, rij, as we defined it, depends on ri minus rj. So that means that if I work out rij squared, that is just ri squared plus rj squared minus 2 ri dotted with rj. And now if I want to differentiate with respect to the alpha component of dri, so let me say alpha is either x, y, or z, and d by d ri, and then the alpha component. So that then gives me 2 rij d rij by d ri alpha component. That's just equal to 2 ri alpha plus 0 minus 2 rj alpha, just from here, so that this term goes away, this term gives you this coefficient, I get the 2 from differentiating this term, and so what I find is that this is just equal to 2 ri minus rj, and this is the alpha component. So I and j are labeling the particles, and alpha is just labeling the x, y, and z coordinates. Okay, so great. So what that simply means also is that if I write this down as in vector notation, then that means that d rij minus d ri is equal to rij over the absolute value of rij, which is just the vector rij over the scalar of rij. Okay, so completely trivial. And similarly, if I did this with respect to drj, then by just changing this, that just gives me a change of sign. So I get rij over rij. Okay, so it's just a normal, a unit vector in that particular direction. So then what I can do is I can write the change in the virial. So there's my fancy V, got it a bit better that time. That's just minus the sum over I not equal to j, Ri dotted with Rij over Rij, and this is a vector and this is a scalar, and then times du by drij. So okay, so we're making progress because now everything is more or less in terms of Rij except for this term over here. So now let's see what we can do about that. So this expression is somewhat is somewhat not symmetric between I and j. I've got an Ri over here, but I don't have an Rj. So I'm going to write this in the following way. I'm going to write this as minus 1/2, and then I'm going to add a term which is the same thing. So I'm going to write it like this: I not equal to j. I'm going to write this as Ri dotted with du by dri plus rj dotted with du by drj. So that's my initial expression. And then I can write that following through the same algebra that we've done over here. I can write this as minus 1/2 the sum over I not equal to j, ri minus rj dotted with Rij over Rij du by drij, like so. And then, of course, this term over here, this term is just Rij, and I've got another Rij up here. So what I'm going to end up with is that I just get minus 1/2 the sum I not equal to j, Rij squared over Rij times du by drij, and then that is just equal to minus 1/2 the sum over I not equal to j, Rij times du by drij. And now mission accomplished. Now we have everything in terms of just the variable Rij. So I just have this and this. I don't have any Ri's or Rj's on their own. So that's as it should be. Okay, so now the next step is that we're going to see how this is related to the correlation function. Okay, so let me now go ahead and introduce what we mean by the correlation function. It would help if I had my notes in order here. Oh, there we go. All right. Okay, so now we're going to talk about correlation functions. So what is the idea of a correlation function? So I'm going to make a definition for you. So what we're going to call this thing, we're going to call this thing the pair distribution function. And we're going to call it G of R. And what is this thing? Well, what it answers the following question. You tell me a separation that you want, and I want to know how many particles are there which are separated by that amount. So G of R answers the question. How many particles are separated by this vector? And I'm not just answering that for a snapshot, I'm going to answer that question when the system is in thermal equilibrium. So that's the fundamental question for which the correlation function is the answer to. Okay, so let's see how we can build an object that does this. So of course we want to count how many particles, but actually what we're going to work out is we're going to normalize it in some appropriate way. So let's first of all count the particles. So the way we count the particles in statistical mechanics is by using delta functions. So let's write this down in terms of delta functions. So we're going to use delta functions to do the counting. So what that means is we're going to start off by saying, you tell me what the R is, and then I've got two particles. They're separated by a certain distance. So that distance is Ri minus Rj. And then I'm going to have a delta function that if Ri minus Rj is equal to the R that you are specifying, then that delta function will give you a delta function blip. Then we're going to average this in thermal equilibrium, and then we're going to sum over all pairs of particles. And then what we want to do is we want to normalize this in the appropriate way. So the normalization we're going to use is this. We know that this quantity here, this delta function, has units of inverse volume because it's a delta function of a vector in three-dimensional space. So to make it dimensionless, we're going to multiply by the volume. And then how many terms are there in the sum? Well, there's n times n minus 1. And then this is going to define for us g of r. So let's just write that down. So this normalization here is the number of terms in the sum. This factor of v is because the delta function has units of 1 over v, and so therefore what that means is that this quantity is now dimensionless. So it's dimensionless and it doesn't scale as we take n going to infinity because of the dividing by the factors of n. So then, and this object here is the thing that does the counting. So that's all that the pair distribution function is, or the 2-point correlation function is. So now we can write this down in a slightly different way. Let's literally do the integral, and so we're going to write this down in the canonical distribution. So we know how to compute the expectation value in the canonical distribution because we're just going to have to integrate over the coordinates of the particles. So what that says is that g of r is going to be this. It's going to be a factor of v. Then what we're going to do is instead of summing over all these, all the particles over here, instead of summing over all of these, what we're going to do is just choose two particles. So we're going to choose I equals particle 1, j equals particle 2, and then when we do that, sum over all the other particles, that's going to get rid of the factors of n and n minus 1. So what we're going to get then over here is that g is equal to the integral of d3 r1, d3 r2, all the way up to d3 Rn. Our Boltzmann factor, e to the minus beta times the potential energy, the kinetic energy of course cancels out, and then our delta function, and now all we're going to do is choose particles 1 and 2, and then those, because this I and j are just dummy variables, so that just gets rid of the factors of n over n minus 1, and then of course we have to normalize by the partition function, and that's just d3 r1 up to d3 rn e to the minus beta u. Okay, so that's what the pair distribution function is. So now let's write this down in a slightly different way. And so what I'm going to do is I'm going to go back and I'm going to take this expression now for the virial. So we're going to start off with our formula for the virial. So there's our curly V. So this is sum over I and j, and then Rij du by drij. Okay, so that's my formula for the virial. So what I'm going to do is I'm going to do a trick, and the trick is to insert 1 into this formula. And this is a trick that you've doubtless seen before in physics. So the trick is to write 1 in a clever way. And that clever way is this. We're going to write 1 as this, the integral d3r of delta of r minus ri minus rj. Okay, so this is clearly true because if I integrate over r over all space, then eventually it will hit this ri minus rj, and that will just give us 1. So what we're going to do is we're going to take this thing here, and we're going to insert it into this part of the expression for delta v. So let's see what happens when we do that. So then we get that delta v is equal to minus 1/2 the expectation value sum over I not equal to j, integral d3r, so r is just a dummy variable, delta of r minus rij as a vector, then rij as a scalar, du by drij. So that's just sticking it in there. And then what we're going to do is we're going to use the fact that if I take the integral over a delta function, I can replace the rij by r itself. So this thing is just the same as minus 1/2 the sum over I not equal to j, integral d3r, delta of r minus rij. And now what I'm going to do is I'm going to simply replace the rij's by r, because this delta function here just replaces rij by r. So I can write this as r du by dr, like that. And now what I can do is I can take the integral outside of the expectation value. So I can write this like this, minus 1/2 integral d3r r du by dr, like so. And why can I do that? Because this expectation value just acts on the rij's. It doesn't act on the r itself. R is just a dummy variable, so this thing here is just, as far as the sum is concerned, just a number. So I don't need to worry about that. So I can write it as this, and then the expectation value is in here. So this is now the expectation value of I not equal to j delta of r minus rij. Close brackets like this. So all I've done is I've managed to pull this thing out through here. And this, the r value that you see as the dummy variable inside this integral is here. here, obviously, but it's also inside here. So what that means is that I can now write this in the following way. This thing, you'll notice, is nothing more than the two-point correlation function or pair distribution function that we started with on the previous blackboard. So what that means is that I can write this then as taking into account the normalization over here. That means I can write this as minus n times n minus 1 over 2, factor of v, the integral d3r, r du by dr, and then this thing over here is just simply the pair distribution function. And so now we've related the change in the virial to the paired distribution function. Okay, so now we're nearly there. So then we can just summarize that for large n, we can say that delta v is basically equal to minus n squared over 2v, and then do that integral. Well, because over this integral here, the forces are central, so this just depends on r, which is the absolute value of the vector r. So we can do this integral in spherical polars. And so what we simply get then is 4 pi r squared dr, and then r du by dr times the pair distribution function. And this is true, of course, when n is thermodynamically large. So now let's put it all together. So our formula for v is just the ideal v that we already calculated, minus 4 pi n squared over 2v times the integral from 0 to infinity of r cubed du by dr times the pair distribution function g of r dr. And that's the formula for our virial. And then what does the virial theorem tell us? The virial theorem tells us is that this is minus 3n kbt from the virial theorem, the exact result. So now we can write down what the equation of state is, because we already calculated what V ideal is. So we know from what we did in the previous lecture that V ideal, this is just equal to minus 3 times the pressure times the volume. And so putting it all together, what we get is that PV is equal to n kBt times 1 minus a correction, and that correction is 2 pi n over 3 kBt times the integral from 0 to infinity r cubed g of r du by dr. And that is our final result. So this tells us exactly what we wanted. What we found is that the equation of state does indeed involve the pair distribution function. Okay, so that's great. The only problem is that now we have to calculate what the pair distribution function is. And so that's what we're going to do next. Now, what I'm going to do is we're going to do this in a rather formal way. Let me see. There was a question. and the question was this from Schreier, we expect the 2-point correlation function to be a function of the vector R and not just the absolute value, because there may be anisotropy in general. And Schreier, you're absolutely right with your question. That's true. But what we're assuming here is that we're assuming that we have purely central forces. And so U just depends on R itself. And here you are, back over here. This is where we made that assumption. Okay, now you can relax that assumption. There's nothing special about it, but in terms of trying to explain what's going on, it makes it more complicated for no reason. We're going to just do this for assuming that there is isotropy. And to do it when you have an anisotropic system is, it's the same idea, but just the integrals are more complicated. As you're going to see, this formalism is complicated enough as it is. So for now, we're just going to assume everything is isotropic. Okay, so what is the strategy next? So there's two things I'm going to show you. I firmly believe that if you're trying to do a calculation, you can't really do the calculation unless you already know the answer. Okay, so the strategy is never calculate until you know what the answer is. So how are we going to do that? Well, we can make a very simple back of the envelope estimate of what the answer is going to be, and then I'm going to do that for you now. And then what we'll do is then we'll calculate it using diagrammatic perturbation theory. So what we're going to do, the next thing we're going to do is a heuristic argument. And then after that, we're going to use diagrammatic perturbation theory. Okay, so let's do it first of all with heuristics, and in doing so, what I'm going to introduce to you is a quantity known as the second virial coefficient. So what is the basic idea here? So the basic idea is that if we're doing perturbation theory, we have to ask, when is the perturbation theory going to be valid? And the answer is that the perturbation theory is going to be valid when we're as close to an ideal gas as possible. Now, gases can be ideal in two ways. One is that the interaction potential might be very small. The other way is that, of course, the interaction potential might be strong, like a hardcore repulsion, but they hardly ever meet each other, and so the effect of that potential is very weak. And that's the case that we're going to think about. We're going to think about the situation where the particles are bouncing around in the box, but they're so dilute that they hardly ever interact. So the idea then, the basic idea, just to write this down, what I just told you, is that if we're doing perturbation theory, so then when is the interacting gas going to be well approximated by the ideal gas? And then the answer to that question is when either the interaction's weak, which means that the potential is very small, or the density is very low, so that there are few collisions. Okay, so we're going to think that we're going to choose that picture. So let's draw a picture of the box that we're thinking about. So here is our box. And now we have our particles scattered around the box. So here's our particles. And what we're going to do is we're going to assume that all those particles are basically far apart from each other, certainly far apart compared to the range of the interactions between the particles, which we saw last time was given by some kind of Lennard-Jones potential. So what we're going to then assume then is that there's two particles which happen to be very close together. Those particles are particle 1 and particle 2. And then we're going to assume that they are far apart from all the other particles. So what we're going to say then is that at low density, particles 1 and 2 are close compared with the scale set by the Lennard-Jones potential. And that scale was basically the hardcore radius, or R0, or R star. So we're going to assume that those particles are close, and then they are far apart, relatively, from all the other particles. And those other particles are themselves far apart from each other. So what that means is that when we do the integral over the pair distribution function, so here's our pair distribution function. So here you can see that we have the integrals over all the particles, R1, R2 up to n. Here are our two particles which are close. And what we're going to then assume is that in the integral, for G of R, it's going to be dominated by the configurations which are like the ones I've sketched. Okay, so what that means is that for when I do the integrals d3 r3 all the way up to d3 rn, those integrals I can ignore the Boltzmann factor, because it's going to basically just be u is going to be essentially 0, and so the Boltzmann factor is going to be 1. Okay, so for those ones I can do that, but I can't do that for the integrals over r and 2. So those ones I need to take everything into account. So let's then see what that means for the integral as a whole. So let's just look at the numerator. So the numerator is going to look something like this. So it's going to look like the integral d3r1, d3r2, d3r3, all the way up to rn, e to the minus beta over 2, sum over I not equal to j, u, I don't need another kt, one's enough, like that, times our delta function, delta of r minus r1 minus r2. Okay, so that's the things I've got to do. And so now we can factorize this. So this is going to be the product of two terms. So there's going to be the terms integral d3r3 all the way up to d3rn, and those are multiplied just by 1. as we've approximated, and then we have the integral d3r1, d3r2, and that's just now delta of r minus r1 minus r2, like so, e to the minus beta u of r12. Okay, so let me write that a bit bigger. E to the minus beta u of r12, u of r1 minus r2. And so this integral over here now can be worked out. So the first thing I want you to realize, so now we're just going to focus on this integral over here. Okay, so the first thing is this: this is r12. This thing is what we call r12. It's just the difference between r1 minus r2. So here's my claim. My claim is that this integral is equal to v, the volume, times the integral over one of these variables. Let's call it d3r, delta of r minus r, e to the minus beta u of r. So that's my claim. And why do I say that? Well, the answer is as follows. Let's imagine that we put our hand on the blackboard. I could do this. I can't really do this on the screen. Let's suppose we put we forget about the integral d3r1 and we just focus on the integral d3r2. So as far as the integral d3r2 is concerned, this, I can see this isn't going to be quite bright enough, so let's go to this color. As far as the integral over r2 is concerned, r1 is just a constant, okay? So we're holding r1 constant, and we'll do its integral afterwards. Okay, so it's just a number. So now I've got r, which is just a number, and r1, which is just a number. So that means that r and r1 are just numbers in the integral d3r2. Okay, so that's just the integral of this thing over r2, and that's just going to simply give me whatever I get multiplied by this factor here. It's just going to simply replace the delta function by that. So that's going to simply then just give me this variable r. This is r1 minus r2, if you like. So whatever I get, the answer once I've done the integral over r2 will not depend on r1, because we're just integrating over all of space for r2, and that's just going to simply replace r2 by what's up in the exponent. So then now, after I've done that, the next step is do the integral over r1, and it's the integral d3r1 times stuff that doesn't depend on r1. And so therefore, that's going to equal the volume of the system times whatever was the stuff that doesn't depend on r1. Okay, so what does that mean for this particular problem? Well, what it means then is that the thing I started with over here, this numerator, is now equal to the volume of the system times doing this delta function. So if I do this delta function, all it's going to do is replace r with little r. So I'm going to get e to the minus beta times u of r, like so. And then I have the effect from all these terms, and all these terms, how many of them are there? Well, they go from 3 up to n, So there's n minus 2 terms, and each integral just gives me a factor of volume. So I simply get then v to the power n minus 2. Okay, so now I've got the numerator. So now let's compute the denominator. So the denominator is exactly the same thing, except that we don't have the delta function. So the denominator is e to the minus beta over 2, sum over I not equal to j, u over kt. That's my factor of beta. Don't need the kt again. And then I have my product of terms, I equals 1 to n, d3 ri. But now there's no delta function here in the denominator. And the delta function was the thing that was holding the particles close together, as you can see over here. That was what the delta function gave us. So what that means is that in this integral, all I have to do is I can ignore the Boltzmann factor, because all the particles are far apart. Not just the previous n minus 2 of them. And so then what I therefore get is that the denominator is approximately equal to the volume of the system raised to the power n. So now if we put it all together, then what we've got is the formula that the pair distribution function is just count all the factors of n is just equal to e to the minus beta u of r. And let's just see where the factors of v went. So over here we have v to the n minus 1 factors. We have this one, n minus 2, and this factor over here. But then in the definition of the 2-point correlation function, wherever it is, there it is. In the definition of the 2-point correlation function, we also have this term over here, this extra factor of v. So when you put it all together, what you end up with then is that they all cancel, and I just get that g is equal to e to the minus beta u of r. So that's really a very nice result. It tells us that we can approximate the pair distribution function. If I know the potential, then I can work out what the pair distribution function is. All right. So now let's go ahead and plot what that looks like. So here is r. Here is the 2-point function, the pair distribution function, like so, and here is the value 1. Here is the value 0. Now, what does this thing look like? Well, we know that as we go far apart from as the particles get far and further apart. Oh wait, there's a question. Is there a question? Could you move the previous slide onto the left side, please? Well, I think I already did that. I think I forgot a few minutes ago. So I think we're good, right? Yep, good, thanks. Okay, yep. I don't always look up at the screen because my camera is right in front of the screen. So if you need to get my attention quickly, unmute your microphone and yell out. All right, so what does this thing look like? Well, we know that as the particles get far enough apart, they're going to look like an ideal gas. So we know that the pair distribution function should go like that. And we know that that's true because u of r, as you go to infinity, u goes to 0, and then this function goes to 1. Okay, so what does this thing look like? So it's going to look like this. There we go, something like so. And this height here is just going to be e to the epsilon naught over kbt, and this scale over here is the scale r naught. And why does it look like this? Well, let's go back a million years. Let's see if we can find it quickly. Maybe we can. Yeah, here we go. So here is u of r. So you can see that u of r goes to 0 as r goes to infinity, and then because it has this structure here with the binding energy like so, then when you take the exponential of that and minus it, you're going to get the thing I've drawn on the right hand side. Somebody asked a question, Vaibhav asks, is this derivation based on the fact that the probability of two particles being very close is very large compared to three or more particles coming together? And the answer is yes, absolutely. So as the particles are very dilute, it's very rare for them to collide. It's even rarer for three particles to collide. So exactly, we are definitely assuming that. So I'm going to say more about that in a couple of minutes. So thanks for the question. Okay, so let's go back to our previous blackboard. This is something that you can't really do in a lecture room, isn't it? You can't just sort of scroll back an infinite distance. Okay, so let's leave it like this. Oh no, I've got one more thing I want to say. So then I want to add another detail here. So what you can see happening over here is that the correlation is small. So this in this region over here, sometimes we'll call this a correlation hole. Why? Well, because the particles are repelling each other due to the hardcore repulsion, and so it's very difficult for them to get very close together. And so this tells you that there's a hole near on scales smaller than R naught, and then of course what that means is there's a corresponding peak at about the mean separation. So there's a correlation hole there. And so where are you most likely to find a particle? Well, you're most likely to find them very close together, like so. Okay, so that's the structure of the two-point correlation function. So the next thing I want to do is I want to take this formula that we've just derived for G of R and put it into our formula for the equation of state. And in fact, we can actually do the integral very easily. So let me write the virial equation of state in the following way. So PV over NKT is equal to 1 minus 2 pi n over 3 kBt. And then what I have is the integral from 0 to infinity r cubed du by dr e to the minus u over kBt dr. Okay, so that's our formula. And if I were to say, well, what are the corrections to this formula? Well, this is a first term in the density, the particle number density n over v. So we would expect that the next terms would be of order n squared, and we're going to see that that is indeed the case. So this is the first term. So this is the low density expansion. And then this is what's the correction to that. So higher order terms. Okay, so now what we can do is this integral we can do by parts. So we're going to write this as a power series in little n and do the integral by parts. So we're going to write it like this. So P over KBT. So here I've got the factor n over v, so this thing is equal to 1 over little n. So then this is going to be, the first term is going to be n. The second term then, which is this one, is now going to be an n squared term. And I'm going to write the coefficient in front of it. I'm going to call it B2. And because it depends on the temperature because of the Boltzmann factor in here, then this is B2 of T. And then the correction term is just going to be a term which is of order n cubed. So we're going to write it like that. And this quantity over here, we call the second virial coefficient. And what is it? Well, let's write it down. It's just this. B2 is equal to minus 2 pi over 3 kBt, the integral from 0 to infinity, r cubed du by dr e to the minus beta u dr. And I can do something really sneaky. What I'm going to do is I'm going to simply add to this expression this is fine. I'm going to do this in the following way. I'm going to add to this expression. I'm going to integrate by, let me just do the integration by parts. So 2 pi over 3, the integral from 0 to infinity, r cubed. And now this term over here is obviously a perfect derivative. So I can write this as d by dr of e to the minus u over kBt. You can see if I differentiate with respect to r, I'm going to bring down this factor of du by dr. So I'll bring that down when I differentiate, and there'll be a factor of kBt, and that factor of kBt will cancel that factor of kBt in the front there. So that's what's going to happen. So I can write this like this, but what I'm going to do is I'm going to do something super sneaky. I'm going to subtract a constant. And the constant I'm going to subtract is 1. Okay, so that's the dirty trick. And then I'm going to integral dr. So why do I do this? Well, d by dr of 1, of course, is equal to 0. But what that means is that this enables me to make the integration by parts very simple. So now I do the integration by parts. So what I get then is 2 pi over 3. So integration by parts says, first of all, I take this term times whatever is in the derivative. So it's going to be r cubed times e to the minus beta u of r minus 1, this tricky one that I put in. You'll see why in just a second. From 0 to infinity, minus, and now I take the derivative, and this derivative now acts on this derivative is now going to act on the r cubed term over here. So when I do that, what I'm going to get is 3 r squared times e to the minus beta u minus 1 dr, and then close my brackets. Okay, so now let's look at this term over here. So this is where you can see why this was a clever trick. So if I evaluate this at infinity, then this thing is equal to e to the minus u goes to 0, so this thing goes to 1, so 1 minus 1 is equal to 0. So evaluated at the upper limit, I get that this thing is equal to 0. And then if I go to the lower limit, when r is equal to 0, so I go to this limit, then this term over here is equal to 0. So this whole expression is actually equal to 0. And so the only thing I have left is this thing. This is the only non-zero part. Okay, so I see somebody has a question. This virial, Shreya says, this virial expansion also looks like that of a quantum correction to, say, the classical gas for bosons or fermions. Does it make sense to compute a two-point correlation function for non-interacting fermions and bosons? So the effects of quantum statistics can indeed be interpreted as a U. So the answer is basically yes. That's it. You can do that. So yeah, good point. So again, that just reinforces the point that quantum statistics looks like a weird kind of potential. Okay, so let's put it all together. So this thing B2 of t is equal to minus 1/2 the integral 4 pi r squared dr times e to the minus beta u minus 1. And I can then just write this as minus 1/2 the integral d3r e to the minus beta u of r. So this then is a generalization to interpreting this, and this this thing is the second virial coefficient, and this is now then our final result. So we've now computed the equation of states. So we now have a good calculation for the equation of state with this thing B2 depending on t, and it depends on t through this beta here, and the integral over r is just some dummy variable, so you just do the integral, and what you get left is something that depends upon kbt. Okay, so what does this look like? So let's plot it. So I'm going to plot B2, and we can see that it has units of volume because it's integral d3r, some stuff that's dimensionless. So I'm going to normalize it by r star cubed, and then I'm going to plot it as a function of kbt. The kbt is dimensionful, so we have to divide by a scale, and the scale that we're going to use is the binding energy epsilon. As always, whenever we draw a graph, we can only plot numbers which are dimensionless quantities. So this is 0, so 1, 2, 3, 4, 5, something like this. And now if you go and evaluate this, you can sort of roughly see what it's going to look like. It turns out to look something like this. And this scale up here, this is equal to 1. Okay, so that's what it looks like. And so you can see that over here, it is positive. And so the pressure is greater than ideal. Over here, it's negative. So when I say over here, that's not over here. Over here, it's negative, and so that means that the pressure is less than the ideal. And then there's a special point where B2 is equal to 0. And that is a special temperature. That temperature is called B2 of TB is equal to 0. So we'll call that temperature TB. That's what that is. And that temperature is called the Boyle temperature. So what's special about this Boyle temperature? Well, what's special about it is that if I write down what the equation of state is, it's PV over NKBT is equal to 1. And then what's going to happen is this second virial term is going to vanish. So then I'm going to get only a correction that is of order n cubed. And so what that means is that at the Boyle temperature, the interacting gas behaves very well like an ideal gas. And so that's what, since the ideal gas law is sometimes known as Boyle's law, so that's why we call this thing the Boyle temperature. So any questions about this? So this is as far as we can go heuristically. Somebody has a question. Let me just read it. So what temperature range is this valid for? You mean this expansion? What temperature range? This is going to be valid at temperatures quite high compared to the critical temperature, or where there's a critical point. So we will actually talk about that in some detail after we've done the diagrammatic perturbation theory. But the Boyle temperature is some special temperature which just depends on the actual interactions of that particular gas. Okay, so let's move on. Let's go on to the next topic, which is the formalization of this. So we're just going to get it started today, and this was going to lead into the lecture from hell, which will be next Monday's lecture. So let's get started by getting this thing set up. So the goal in this section is now a systematic procedure to calculate the non-ideal corrections to the equation of state. So what we're going to do is we're going to write down the virial expansion. So when I say the words virial expansion, what I mean is this. I'm going to say that the pressure over kBt can be written down as an expansion in terms of the density. So there'll be a second virial coefficient, a third virial coefficient, and so on and so forth. So this, the calculation is, how do I put it? Calculation is fantastically awful. And what we're going to see is that we can break it down, but very beautiful. And the reason it's very beautiful is that we can break it down into components that have nothing at all to do with a particular system of interest. In fact, we're going to see that any interacting system will follow the same graph theoretic procedures. So we're going to break it into components that don't really depend on U itself. And what they do depend on is combinatorial factors. And it's the combinatorics of the many ways that particles can interact. And so this is a prototype of Feynman diagrams. So we represent these possible interactions by diagrams, or graphs, we sometimes call them. And these are shortcuts to represent the integrals that we need to do. So remember that B2 was an integral. And so we'll see that B2 is an integral, B3 is an integral, and so on and so forth. And the structure of those integrals can be written down in a way that doesn't depend on what the potential is. It just depends on the way that the particles connect. So there's going to be two pieces of magic in this calculation. So the way I like to describe this, the way I think about it is this. I like to go hiking when I go on holiday, and I will typically, when my children were little, we would take them on hikes in the mountains of England, and we would refer to these hikes as death marches because they would often be long. They'd be in very bad weather usually, and we'd often get lost, or our map would be wrong, or something like this. And so they would be quite challenging, especially when our children were little. Of course, it's a bit of drudgery, but every now and then you get to the top of a mountain, and then you have a beautiful view, and you can say, aha, this was worthwhile. And then you sit down and eat your sandwiches and have a nice time, and then you get ready to trudge back down the other side of the mountain. So this calculation is a little bit like that. And there are two particular vistas that I want to that I'll point out to you as we go along. So there's two pieces of magic. So go to sleep, trudge along, and I'll wake you up when we get to a nice view. Okay, so what are those nice views? Well, why do we do this? So you might ask, well, why are we bothering with all this? And that's a perfectly good question to ask. And the answer is, yeah, you're right. Good question. And it's a good question because the answer that we're going to get is very boring. So we're not doing this because the answer is especially interesting. We're doing this because the techniques are general. And apply to all interacting systems. So they can be interacting systems in statistical mechanics, in quantum field theory, and so on and so forth. These are even string theory. So these things are general. And the particular techniques that we're going to see is we're going to see that there's a thing called the cumulant expansion. We're going to see that there's a thing called the linked cluster theorem. And then we're going to see that there's one other magical cancellation. And all of these things are general and just depend on the topology of these graphs. So they don't depend on the values of the integrals. Okay, so these are very general things. So now let's get it set up. We have a few more minutes left. Actually, we don't have any minutes left. It's 3:21. So I think rather than get it started, I will leave that to next time. So this will be so we won't we'll quit here, and we'll start with this, the lecture from hell, next Monday. Okay, so that's it. Are there any other questions before we finish?